Our next presenters are Alicia Deal and Clayton Nicolardi. Dr. Alicia Deal is a drinking water specialist with a master's and PhD in drinking water treatment. Starting in 1997, she worked for the TCEQ in various compliance and assistance roles. Since retiring in 2016, she has been a contractor on the Texas Optimization Program. Mr. Nicolardi is a senior engineer with the TCEQ's Office of Water Supply Division, Emergency Preparedness and Response Section. He is a graduate of the University of Texas at Austin and a U.S. Army veteran. He has worked for the TCEQ for 18 years, 16 of which have been spent assisting public water systems across Texas. Clayton is also a licensed surface water treatment plant operator and has worked in the private sector as an operator and consulting engineer. He enjoys hobbies such as spending time with family, hunting, and fishing. Please welcome Alicia Deal and Clayton Nicolardi.
Good afternoon. Welcome back after, I hope, what was a really good lunch. And if you're not from Austin, welcome to Austin. We're going to talk about chloramines. How many of you have already been to this presentation once, like last year? Yeah, well, it hasn't changed a whole lot, thank goodness. I mean, it would be a bad thing if it changed every year, and I like to say, you know, once I've given this presentation about 4 or 5 times, I'm hoping that I start to understand it. So I get it. But it is kind of, this one is driven towards just the basics. Tomorrow morning, one of the workshops that Christina mentioned, the first one is a tabletop where we'll actually get into a nitrification action plan and try and figure it out and make changes. And then the last one is called advanced chloramination. So go ahead and store up some of your really tough questions. We'll try and answer them today, but if you don't get them answered, come on tomorrow. So let's go ahead and look at what we're talking about. First of all, just a few slides about the history and background of chloramination in Texas. And then the breakpoint curve. The breakpoint curve is what we live and die by with chloramination, right? We'll put this over to Clayton, let him talk about sample collection and analysis, and then sites and schedules. Kind of all the basics. So first of all, what is or what are these chloramines that people keep talking about all the time? So start with Texas, I think Texas is right to do this. Texas requires that all distribution systems have what? A residual disinfectant in their distribution system. Because why? Because otherwise you could have bugs either persisting throughout the whole system or regrowing in some little, tubercule or crack or something. And so having that disinfectant in the distribution pipes is what kills out those potential pathogens, which is key. Now, does every state in the United States do that? No. Only not even half of the states require this. And I think it's really smart. So yay, Texas. So when we talk about that distribution residual, of course, where it all started was kind of free chlorine. Free chlorine is knocks it all out. And when we say free chlorine, what we mean is the family of free chlorine, which means hypochlorous acid and hypochlorite ion. There's 2 members of the free chlorine family. And when you measure free chlorine, that's what you measure. Okay? Free chlorine means this plus that, hypochlorous acid plus hypochlorite ion. But the disinfectant in that family is actually hypochlorous acid. Do you think hypochlorous acid is going to be more likely to be there at low pH or at high pH? Right, low pH, right? It's an acid, low pH is acidic. So for free chlorine, that hypochlorous acid family member is there at low pH. Now, there's also a family of chloramines. When we throw free chlorine together with ammonia, it reacts really fast and it forms this family of chloramines. And just like with the free chlorine family, some of these family members are great, others not so great. So we got monochloramine. Monochloramine is the disinfectant. It's what we want. It's like you're having Thanksgiving dinner, and monochloramine is your cousin who comes over and brings a really delicious side dish, and as soon as you yawn one time, she's like out the door, right? And then dichloramine also forms. Well, dichloramine is not so great. Dichloramine comes in late. They've been at another party and they kind of smell like they've been drinking all afternoon. They eat all the turkey and then they split. So they're not that great. Trichloramine. You don't want trichloramine. Trichloramine comes in, doesn't bring a side, comes in immediately, drinks all your beer, and falls asleep on your couch, and just makes a mess, and you would just assume that trichloramine never came to Thanksgiving again. So when we say chloramines, we mean that whole family, but the only member of the family that we really like and care about and want is monochloramine. And so that's usually what we mean. Well, in Texas, chloramines have been used for a really long time. Other states might have a different practice. We've had chloramines in systems for a long time. For instance, Austin started chloraminating in the 50s, actually, and did a great job and has done so ever since. What happened, of course, as some of you remember, some of you are almost as old as me, but much better looking. Surface water treatment plants and all systems came under the trihalomethane rule in 1986, and all of a sudden, free chlorine didn't look quite as attractive because it formed these regulated, potentially cancer-causing, these trihalomethanes that we didn't want. And so people started using chloramines because chloramines don't form those trihalomethanes and haloacetic acids as badly. When we got the trihalomethane rule, well, of course, that was just the start of things, right? Then we had the first disinfection byproduct rule in right around 2002 or 2000, it started hitting systems. And then, of course, we had DBP2, the second one, and that started hitting people in the mid-00s, right? And to the 14 time frame for smaller systems. And I used to say, and I hope we never have DBP3, but in fact, not this year, but maybe in a couple of years, we're going to be hearing something about DBP3 from the EPA. So, darn it, didn't retire soon enough. So because of those, the disinfection byproducts, most of the 400 surface water treatment plants in Texas chloraminate. And then, of course, those surface water treatment plants, a lot of them sell water downstream. How many of y'all are at a purchased water system that has chloramines? Okay, and I'll double that to add the people that if you told them you'd give them $20 for raising their hand, they still wouldn't raise their hand. Yes. But it's a lot of systems. It's a lot of systems, right, that have chloramines. And so a lot of folks are in the same boat as you. And, it can be a pretty rocky boat. Has anybody come down here from Northeast Texas, maybe around Texarkana, Tyler, Longview, up there, or the Gulf Coast? Anybody down Galveston way? Yeah, Golden Triangle, whatever? Yeah. So we have another problem in those areas. It's a challenge, but y'all are Texans, you can overcome that challenge. That groundwater in Northeast Texas and in the Gulf Coast can have naturally occurring ammonia. Well, if you try and free chlorinate that water, what happens when you add chlorine and ammonia? Chloramines. And so we've got a real challenge there helping groundwater systems in those areas with chloraminated water. So, and another thing about those waters is a pretty high total organic carbon, so that's just a hard water, difficult water to treat anyway. So we got pros and cons, right? One of the pros of chloramines that's really important to us, to Texas, some of you have some really long distribution lines, right? Miles and miles. And chloramines, monochloramine, can last for weeks, literally weeks, as much as a month or more. Free chlorine only lasts for days. And so if you're using free chlorine, there's pipelines, you're just not going to be able to get a residual all the way down that pipeline. A pro rather, a con for free chlorine, a pro for chloramines, doesn't form the trihalomethane, doesn't form the haloacetic acids. Boom, gets you in compliance for a pretty big health-based rule. Now a con is it has a good disinfecting effect. You have to have a little higher residual to get that effect. Then again, it lasts longer, so I think it's going to be a wash in terms of cost. Another con that we'll talk about in our next presentation is the potential risk of nitrification, which, when it happens, we lose that benefit of distribution system disinfection that we want so badly to kill out any potential pathogens, because the nitrification can cause a loss of residual. But the worst con, of course, is having to learn more chemistry. You thought you'd gotten done with this in high school, right? Nope. So let's go ahead and kind of go back in time for a minute and think about how we wound up with this curve that we live and die by with chloramines, the breakpoint curve. So back in the 1930s, how many of y'all have a wastewater license on top of your drinking water license? So it was you guys, it was the wastewater guys that actually figured this out. The wastewater guys, drinking water folks had started chlorinating with free chlorine water in like 1908, 1890, pick your historical fact, okay? But in the 30s, the wastewater guys were like, you know, my river's kind of on fire and stuff, and I'm thinking maybe I should put less bad things into my river. And one of the things they didn't want to do was pass these pathogens down the river anymore, and so they wanted to chlorinate their wastewater. Well, does wastewater have ammonia in it? Licensee? Yeah, it sure does. And so they would chlorinate this water, and they were very confused because they didn't see what they were expecting to see. What they expected to see when they added that free chlorine to the water that already had the ammonia in it was, okay, at that first little line, you'll see a little iron and hydrogen sulfide permanent demand using up some of that chlorine. Okay, that's fine. But then what they'd expect is you put in 1 milligram per liter of chlorine, you get 1 milligram per liter when you test it, right? They didn't see that. What they saw was, as they took this wastewater with ammonia in it and added more and more and more chlorine, they got this weird shaped curve, which instead of going up all the time, had this spot where it dipped down. And these were the wastewater operators. Because they wanted to get to free chlorine, they wanted to have this going up, and so they called that dip the break point, the point at which wastewater operators want to break past that dip. So understanding that curve is key to really understanding what's going on in your system. Some basics, when we usually throw the breakpoint curve up there, what we're talking about, the y-axis is the residual, and the curve we draw is the total chlorine curve. That's the sum, right? That's not just one chemical. Total chlorine doesn't mean one chemical. It means the sum of all active chlorine species. So it reads monochloramine, dichloramine, free chlorine, trichloramine, all active chlorine species. And I'm going to graph ammonia on the curve when we're going through today because it's super useful. The x-axis, where we go down the x-axis, that is how much chlorine we've added in relationship to the ammonia-nitrogen, okay? So the chlorine to ammonia-nitrogen ratio. And if you're getting into this at first, you can think, oh my gosh, you know, either I or the upstream system is putting these two chemicals in, so clearly the chlorine, the amount of chlorine and the amount of ammonia that I dose is going to be super critical to get that chlorine to ammonia-nitrogen ratio correct. So just one little cute slide of making monochloramine. So over here on the left, yeah, I guess, you've got a hypochlorous acid, right? O, oxygen, and then a chlorine, and then one little H on it stuck together. That's going to be hypochlorous acid. And down here, we've got a monochloramine, and I'm actually making dichloramine in this slide, and I apologize to you. This is a slide where we've already got monochloramine, and we're making dichloramine. So sorry about that. What I wanted to show you was that when you add hypochlorous acid to ammonia, just the little ammonia, that you actually make monochloramine, which is one chlorine, one ammonia, and two hydrogens. Oops. And they're really fun to watch. I'm a picture person. If I can't draw a picture of it, I probably don't understand it. But this was dichloramine. So let's try this one. So Yufeng Xia, Professor Xia, he is a professor in Pennsylvania, and he was like, well, how can I explain making monochloramine to people? Well, the people that he's working with, they might go to the bar once in a while, okay? So he says, okay, we've got the chloramine bar, all right? And at this chloramine bar, there's a lot of little seats all along the bar. And at about, 8 in the evening, all the ammonias, they've got their hydrogens all arranged neatly, and they've all gotten ready, and they all go out to the chloramine bar, and they find a place to sit. And at about 9, a chlorine walks in, and that chlorine is like, oh, I really like that ammonia over in the corner. I'm going to react with that ammonia, and we're going to make monochloramine and get along very well. And so maybe about 10, another chlorine walks in and finds the cutest ammonia in the bar, and they get to react and talk and chat. And at 10:30, at 11, another chlorine, 11:30, and now every ammonia has had the chance to react with one chlorine, right? Monochloramine. Everything's fine, right? It's perfect. But now it's 12:30, and another bar lets out, and another chlorine walks in. And that's when the fights break out. That chlorine has nobody to react with. So the chlorine's going to get in a fight with some other chlorine so that they can get a hold of some ammonia. Well, that's not going to work. All the ammonias are just going to leave. And that's what we're going to talk about on the breakpoint curve. So we're going to talk about the zones on the breakpoint curve, okay? And think about the bar theory. So this is before the zone 1 is before the bar even opens. We've got that hydrogen sulfide, that iron, maybe manganese, maybe in East Texas, and actually all over you've got different water that could have manganese in it. It could depend on your intake. And we've added a little chlorine, but it reacts super rapidly with those permanent demand chemicals that just use it up. So we get zero residual for a little bit that we're adding chlorine, okay? It's used up. And that's zone 1. So the bar hasn't even opened. Now the bar is going to open, and we're going to be in zone 2. And this is from 8 o'clock until 12, where we're able to match up one ammonia with one chlorine. So in zone 2, we're adding the chlorine, and there's an ammonia available to react with it, and we're making monochloramine. And actually, truthfully, the slope of that curve in this zone, in zone 2, is about 1-to-1. We add a milligram per liter of free chlorine, we get a milligram per liter of monochloramine. We still have some free ammonia. You see that dotted gray line down there? We still got some ammonia in this zone. It hasn't been used up until we get to the mountain, right? And so now let's go to 12:30 at bar time. And we're going to have zone 3. That other chlorine is going to walk in, and there's going to be a fight. So dichloramine is going to be formed. Trichloramine is going to be formed. But those things are super unstable, super stinky, the Thanksgiving guests that you don't want to have be there. And when they decay, they drive the nitrogen out of the water, mainly as nitrogen. So zone 3 is where you've got unstable chloramines. It's a bad place to be in. Zone 4, this is the wastewater operator's dream. You've driven off all the ammonia, so you have no monochloramine, you have no ammonia. All you've got left is the free chlorine that you're adding. And for wastewater, if you wanted to achieve a free chlorine residual, this is where you've passed the breakpoint dip and you're into the free chlorine zone. So there's free chlorine past the breakpoint dip. Do we want to be here? No. If we were here, we'd be making DBPs again. We'd be back where we were when we were chlorinating as opposed to chloraminating. So I'm going to turn this over now to my esteemed colleague, Mr. Clayton Q. Nicolardi, PE, ABC, QRS. You need a clicker?
Clicker.
Oh, well, I guess. That'll
Thank
be
you.
$5, please.
Thank you. Hey, I'm already finished. Thank you so much for that applause. And good job, Alicia. So picking up where Alicia left off, I'm going to talk about chloramine effectiveness sampling, which is very important. You typically don't want our team coming out and helping you deal with nitrification issues, boil water notices and do not use or do not consume orders because of high nitrite and the like. So hopefully you'll learn a great deal from this presentation and from workshops that are occur tomorrow. So free chlorine versus total chlorine. Free chlorine analysis measures both family members, hypochlorous acid and hypochlorite ion, which Dr. Dill already mentioned. But the DPD method for free chlorine also will pick up manganese interference, and monochloramine is an interference for the DPD method for free chlorine, okay? Total chlorine analysis measures all the chloramine species, the members of the chloramine family, and both free chlorine and total chlorine measure as chlorine. So let's talk about this breakpoint curve. Alicia showed several slides describing this breakpoint curve. The total chlorine breakpoint curve is really the sum of all these curves, the chloramine species, free chlorine, and yes, also organic chloramines or organamines. And sometimes that's hard for me to say, but it measures all of those species. So we're going to talk a little bit about the breakpoint curve. Again, on the y-axis, this is the total chlorine residual, and this is the chlorine to ammonia's nitrogen mass ratio down here on the y-axis, on the x-axis. So monochloramine, anything 5, really less than 5 to 1, is going to be predominantly monochloramine, okay? And that's what you're seeing on this graph now. Dichloramine, when you exceed the 5 to 1, so somewhere in between 5 to 1 and 10 to 1, you form dichloramine and trichloramine. So that's not where you want to be. That's kind of the dirty sock smell. That's the fleeting residuals. That's having, a good residual, 5 hours before and all of a sudden it's gone. And so that's not where you want to be. And plus, the issues with nitrification, potential nitrification. And then once we go past 10 to 1, usually approximately 10 to 1 on the ratio is when we hit breakpoint. So if we continue to feed free chlorine and all the ammonia is gone, we'll begin to oxidize mono and the di and trichloramine and organic amines or chloramines. Then we'll eventually go past breakpoint and run a free chlorine residual, which some folks, if you don't have a lot of organics in the water, precursors to DBPs, then that may be appropriate. But for a lot of us, especially where I live in East Texas, it's not. And then here, this graph is total chlorine, and again, that includes all those chloramine species as well as free chlorine. So, question, what can we measure to figure out which zone we are in? Because Dr. Dill talked about really 4 zones. You can't really, we've taken out demand. Demand is the first zone, really. There's 4 zones. So that first zone you won't see on this graph. We've taken it out. So there's no demand. Zone 2 is just kind of monochloramine, where we're producing monochloramine by adding chlorine and having ammonia present. And this is a 3rd zone, and the 4th zone is free chlorine. So, but what do we need to measure? What's the chloramine effectiveness samples, and what do we need to measure to identify where we are on this chlorine curve? That's the question. Well, we can't measure dichloramine and trichloramine because they're very volatile. So you can't do that in a field test. And Dr. Dill's done a lot of research, and maybe in the laboratory it's even difficult to measure di- and trichloramine.
It's a pain.
Okay? So you can't measure those. So that's out of the picture. We'll get rid of those. You can measure total chlorine, monochloramine, and free chlorine, but you can also measure free available ammonia. Okay? And we have testing equipment. Many of you probably have that equipment. So we can measure these parameters. Now we're going to do a little test here. So if we were to have a total chlorine residual, if I told you it was 1.5 milligrams per liter, and I asked you where on this chlorine curve, if this is chlorine residual on the y-axis, 1.5 is right here. But if I asked you where on this chlorine curve you were, could you answer the question? With just measuring total chlorine? Well, no, you can't. Okay? So there's that 1.5 residual. So where are you on that curve? Okay? Hit the one in the middle, right? Hit the one in the middle. So maybe this goes with the bar theory, Alicia. Hit the one in the middle. So this is what you're left with when you only measure for total chlorine. We go to multiple systems that have nitrification, and we find out that all they're measuring is total chlorine when they're chloraminating. And so they have no clue, because total chlorine only gives you, a mixed solution here. You don't know where you are on that curve. But what if we were to add, we monitored monochloramine and we got a 1.2 residual. So total is 1.5. We do monochloramine, we get a 1.2. Okay? So now could you tell me where you are on that total chlorine curve? Well, it kind of narrows it down. So now you can't hit the one in the middle. So you got to pick 50-50, right? One on the left or one on the right. All right? So we've done total, we've done mono. All right? So we can knock that one that just left the screen, we can knock it out. Process of elimination. But now what if we measured free ammonia? And that free available ammonia was a 0.3. Well, that begins to tell us a little bit more of the story. So 0.3 is about right there on the graph, okay? So can you tell me now if the free available ammonia is a 0.3? You know it can't be past this 0.5 or this 5 to 1 because there's no ammonia right there. So 0.3 is right there. So now does that give you a little bit more clue to where we are? Well, yes. Now we can tell where we are on the chlorine curve. And again, as Dr. Dill mentioned, we want to be on that front side of that curve when we're chloraminating. We don't want to be on this downslope. Think of going down as bad. Okay, it's kind of like going up that roller coaster, click, 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 that my son begged me to get on, and then he wanted to get off of it. I said, it's too late, son. You got me in this predicament. You're going to sit here with me. Okay, so what do we measure? Or what do you need to measure? That's the question. That's a question of you. So mentally, you don't have to speak it out and embarrass yourself, but make a mental picture. Total chlorine, monochloramine, and free available ammonia. And these are the chemicals that we refer to as chloramine effectiveness samples. And when you do workshops tomorrow, you'll go into great level of detail on that, okay? So anytime somebody asks you if you're doing chloramine effectiveness sample and you say, what are you talking about, Willis? Did y'all ever watch Different Strokes? I mean, I'm kind of aging myself here. This, I'm a hand model now, and I didn't realize that. You know Joey on Friends? You know, he was the hand model. So I don't know if Alicia took this or not, but anyway, this is me taking chloramine effectiveness samples with an SL1000. All right. So common methods, DPD and endophenol. Now you may call that endophenol or whatever, endophenol. I really don't know what's the appropriate pronunciation, but there's DPD for total and free chlorine. So that gives you the reddish color. You all don't know if you're familiar with the endophenol method. When you do monochloramine in your free available ammonia, you use the endophenol method. There's also a endophenol method for doing free chlorine, which takes out the interferences associated with monochloramine and, yes, manganese. If you guys aren't familiar with it, ask one of us. In a workshop after this presentation, I may even have some of the reagents with me. I'm not sure, but maybe I do. Accurate data leads to good decisions. Would y'all agree? No data leads to poor decision making. The more data we have, the better decisions we can make. So make sure you're using consistent and technically a sound approach when you're sampling method. We often see when we go out to the field, we'll just kind of watch out of the corner of our eye. We'll take the samples. We'll also watch operators collect the samples. What we're looking for is we're looking for consistency in sampling technique, but we're also making sure that that follows the manufacturer's specifications and guidelines for sampling. Use instruments with the required minimum accuracy. And so if you have any questions about the equipment you're using, please reach out to our technical team. We can help. Follow the method exactly. Make sure that the glassware is clean. I don't know how many times I've gone out in the field where the glassware is scratched, where the plastic cuvettes used for doing mono and free available ammonia, or even total and free chlorine are black. If you leave the reagent in there, they kind of turn black. They delaminate, they cause a lot. That's a colorimetric method. So you think about it, you're shooting a beam of LED light through there. And so any kind of imperfections in the cuvettes, the glass or plastic could cause an issue. When you're collecting samples, make sure that you're taking a representative sample. When we say representative, that means we want main water. We want the water that's coming out of your main. So you need to at least flush 2 volumes through the sample line to make sure. You can feel for temperature change. That's what I often do when I'm flushing, but you don't want to overflush. So if I'm flushing so hard, like 2,000 gallons a minute at a fire hydrant, and everybody's pressure drops below 20 psi, bad. I've seen it happen. But if I'm, measuring the water, 2 miles down the road, that's not what you want to do. So what we see often in the field is if a lot of these equipments like the DR 1900, 900, 850, whatever you're using, 300, they have an upper range on free available ammonia of 0.55. If it blinks and it says over range, do a dilution. Take some distilled water, do a dilution. If you don't know how to, reach out to one of us and we can help with that. But just to write greater than 0.55 tells us absolutely nothing. What if the ammonia is 1.5? I mean, I've seen it as high as 2. I don't know. I'm sure some of the team members have seen maybe even higher. When you're picking sample sites, make sure it's they're representative of the distribution system. Okay? When we talk about process management, it's how we manage the process. It's how we manage the chloramination process. Okay? Regulatory-wise, total chlorine monitoring may not identify issues. When I talked about earlier that total chlorine doesn't really tell you much, the graph showed you that. Hit the one in the middle. So total chlorine really doesn't tell us anything. But it's the combination of total, mono, and free available ammonia and that data which helps us make the right decisions. So your process management sampling for mono ammonia can identify problems before they even start. And isn't that what we want to do? Because the last thing we want to have to do is issue a boil water notice, right? If you're a water system, that is like the last thing that we want to do. The minimum sampling requirements, this is the table showing those, okay? So for total chlorine, we need to do at least weekly. Mono, same, free available ammonia. The first 6 months is when we sample for nitrite and nitrate to get a baseline. Then after that, in response to action triggers, and we at least do quarterly. But Alicia highlighted these, and the reason why we do this is it says at least. But you'll notice that some of our rules say at least or more often to maintain water quality. Get what I said? At least or more often to maintain water quality. So that means that one system may could get away with a weekly sample, whereas another system may have to do it daily. Does that make sense? If I'm purchasing chlorinated water from another system and it's fluctuating, and I'm trying to base my chemical feed on what I'm getting from the purchase water, from the wholesaler, then daily samples may be in order. Y'all with me? So daily samples may be required there. Sample sites. We want to look at raw water. Some raw water has got ammonia in it, believe it or not. That's a joke. I mean, and a lot of this depends on where you are in the state. It really does. State of Texas has all kinds of different water. But, so you need to check your source water. You may have ammonia in your source water. You may be chloraminating and not even know it. And that's a huge issue in the state. Before and after dosing, I mean, that makes sense. If we're going to dose a chemical, we need to be able to take a sample and find out where we are on that curve. Find out if we need to, adjust this chemical, feed more chlorine, feed less LES, vice versa, and then distribution samples. Okay, what are critical points? Well, critical points may be an elevated storage tank, but they're locations where water quality changes or where critical data is available. That may be a high water age site, maybe a low water age site. Sources, plants, entry points are critical. Distribution system, in the distribution system may be an elevated storage tank. ESTs that are floating on the system, y'all with me? You gotta have them, but aren't the ones that float on the system dickens of a problem to deal with? All right? I know I've got a lot of folks in here, I'm looking at you. I know that you've got a lot of ESTs floating on the system, and they don't deep cycle enough, and so you have issues maybe with maintaining residuals. High water age areas I already talked about, and then pressure planes. You may have multiple pressure planes in your system, and you need to sample in those. All right, so schedules. We really kind of went over the schedules here, so I don't want to beat this down. A spread out system will need more than a single sample per week. Nitrification can take hold in one area. So you can have a balloon, you can have nitrification in just one isolated area. I've done many responses, emergency response, where we had an isolated, pressure plane that was a problem, and maybe they had 4 pressure planes and only one of them had nitrification. And so do you issue a system-wide boil water notice? Well, if you can prove that that's an isolated area, then maybe you don't have to. But you need to monitor in all of those pressure planes, not just one. And this is actually a good schematic. I don't know if Alicia put this together or not, but this to show you these are going to fly in these sample locations. So what do we want you to notice on this is, okay, this is appears to be a dead end. So obviously I'm going to want to look at a dead end, right? I know that I'm supposed to flush all dead ends at least once per month or more often to maintain water quality. Well, I want to sample those locations. You'll notice that this EST is a critical sampling location. I got a pump station here maybe. So this is just kind of give you an idea. And notice how those are spread out. What if all these were just in one side of the system? And we've witnessed that. Where samples were collected, guess what? Well, if I took samples over on the other side of town, I wouldn't get a residual. Well, don't tell me that. Of all things, I mean, then the other guy's over there saying, shut up, shut up. So take home message. Chloramines are an important tool. You know, for many systems, they're the only way we keep, you know, DBP compliance. You know, for some systems, that's all they have. They can't use free chlorine. It helps systems meet maximum contaminant levels for THMs, HA5s, helps maintain stable residuals. What do I mean by stable? You all in here know if you've had nitrification or you've had unstable chloramine, how big a problem that is and how difficult it is to deal with. So you want those stable residuals. Monitoring is key to effective, successful, stable chloramination. If I don't do the process management samples, if I choose not to do that, then I'm not only setting myself up for potential nitrification, but I'm also not allowing myself to make those educated decisions, good decisions. So make sure you're doing total chlorine, monochloramine, and free available ammonia. And that is all. And we've got, what, a couple of minutes maybe for questions?
Thank you, Clayton. We do have a couple minutes for questions. If you are attending virtually, go ahead and throw those into the chat, and we will try and get to them. If we don't, the speakers will respond in writing. And for those here in the room, raise your hand, and I will come over to you so the people online can hear your question.
Yes, sir. We live in a system where we have both mixture of groundwater and surface water. So chloramines and chlorine are a big factor. We had a time where we were mixing the water and we had an ammonia smell in some of the waters. What is that?
Okay, so I believe the question, and correct me if I'm wrong, is so you had a free chlorine, had groundwater system that was free chlorine, you had chloraminated water from a surface plant, and those were blending, and you were having a smell. Well, again, looking at that curve, when you're producing monochloramine up to 5:1, when you continue to add free chlorine to that, then you're oxidizing that and falling on the backside of the curve, forming ditrichloroamine. That's why it's a significantly bad idea to blend free chlorine and chloraminated water. In fact, it requires an exception. Correct me if I'm wrong, guys, but okay. So if anybody tells you that they can blend and not have any problems, the thing is they just don't know any better. Because what happens is you get pockets of no residual moving around in the system. Wherever that, hydraulically, that water does this. So good question, though.